all yours to tell us, and thanks for coming all the way.
Okay, thank you. Good morning, I'm Seung-Yoon Lee from Kyungbu National University, Korea. First, I'd like to thank having me here. I'm happy to join this conference. I learned about the circular economy yesterday, and I could know about the importance of urine as an important source of the fertilizer nutrient. Today, my topic is a bit far from the nutrient extraction, but I hopefully this talk can provide some insight for your research. Okay, let me start my presentation. I'd like to talk about machine learning model to predict the performance of pilot scale FO module. First, let me briefly talk about the connection between the circular economy and forward osmosis technology. The circular economy aims to keep the materials and products in circulation for the sustainable environment. To improve the recovery and extraction efficiency, normally extraction concentration process is used as a pre-treatment process. One of the simplest technology for the concentration process is membrane technology. Membrane can selectively keep the target substances by allowing only water moves through the membrane. The critical point for the normal pressure-driven membrane process is energy and membrane fouling. But for the osmosis technology is different. In FO process, water transport through the membrane by osmosis phenomena from the low concentration side to high concentration side. Here, high concentration solution is called draw solution. Because the physical pressure is not required, so FO process has an advantage in the energy and fouling. Therefore, recently, hybrid FO processes combined with other technology have been studied. For example, here, FO is coupled with reverse electrolysis, and here, this process can simultaneously generate electrical power and fertilize water. And FO can be combined with membrane distillation for the potable water production and fertilizer solution, or FO can be used for the effective watering of microalgae. Most of these researches were conducted in lab scale, and for the upscale of the FO process, prediction of FO membrane performance is required. However, the performance prediction is not simple in a large-scale FO module because the concentration and the flow rate continuously change along the membrane channel due to the water flux and then forward and reverse salt flux. The water and salt flux can be estimated using mass transport parameters, including water permeability and salt permeability, and the other mass transport parameter coefficients. As you can see here, the accurate mathematical modeling is quite complex. So recently, after development of the machine learning, it has been applied to the FO modeling. Although some of the mathematical and the machine learning studies have been conducted, most of these were the lab scale, especially for the machine learning studies. They use the lab scale data. In this study, we tried to develop mathematical and machine learning model for the pilot scale membrane module, and we compared it to the result. We obtained experimental data using the plate and frame membrane module, and we prepared the different concentration of the draw and feed solution using NaCl. And we investigated the effect of the membrane area by changing the number of the element by adjusting the valve of the system, and each membrane element has a 7 square meter membrane area. This is the picture of the actual pilot system. The most mathematical modeling was conducted based on the mass balance equations in cross current flow mode, and we divided the membrane area into number of small segments. And first, we predicted the water flux using the mathematical model, and then we calculated the consequent change of the flow rate and concentrations based on the water flux. The mathematical model was conducted using MATLAB software. This slide shows the structure of the machine learning algorithm. Instead of using transport parameter, machine learning optimizes the relationship between the independent variable by changing the weight, and then it tried to obtain the accurate prediction for the output. Here the output was the membrane flux. We used the membrane area, feed and draw flow rates, and feed and draw concentration and pressure as input variables, and we used the 5 different machine learning algorithms to select the best machine learning algorithm. And then using the best machine learning algorithm, we predicted water flux, and then we also we predicted the operating pressure of the membrane module. This slide shows the 5 different machine learning modules that we used: the multilinear regression and KNN and SVM, and we used it decision tree and artificial neural network, in short, and ANN. First, let's look at the mathematical model result first. To run a mathematical model of one element with 1,000 by 1,000 segments, it took around 30 seconds for one condition. But the mathematical model estimated 52% higher water flux compared to the actual experimental results. Anyway, a mathematical model provided the change of the flux and the change of the draw concentration and feed concentration and the flow rate of draw and feed in each segment consistent with the expected trend along the membrane channel. To improve the prediction efficiency, we tried machine learning. To select the best machine learning algorithm, we compared the I-sphere and RMSE values of the 5 machine learning algorithms. Among these, MLR and SVM and ANN showed good performance in terms of R-sphere and RMSE, and we selected ANN as the best machine learning model, and then we optimized the ANN to improve the accuracy, for example, changing the number of the neurons. This slide shows the measured water flux and then predicted water flux using the ANN. As you can see here, ANN provided very good prediction accuracy. For example, the I-sphere of the ANN was higher than 0.99 when all the data was used. And from the predicted water flux data, we calculated the flow rate of the permeate and flow rate of the draw solution, flow rate of the feed, and we calculated the recovery and we predicted feed and draw concentration. As you can see here, overall the calculated values were very close to the measured value, but we found some interesting point. For example, here, and here, we found some several data which has a relatively high large error. And after examining the experimental data, we found that these data were obtained under the extreme conditions, such as too high flow rate for the membrane module. This means that the machine learning model can be used to identify problems in experimental data. From the measured predicted water flux, we could estimate the water recovery and concentration at the exit of the FRO module under different operating conditions. In addition, with the same independent variables, we try to predict inlet and outlet operating pressure in the membrane module using the ANN. As you expected, and interestingly, ANN model provided very good prediction accuracy for the operating condition too. This result shows the great potential of the machine learning for the real FO system, because the prediction of the operating pressure is very important in the real system, and it is very difficult to predict using the mathematical model. Okay, in this study, we developed mathematical and machine learning model to predict the pilot scale FO membrane module performance. And mathematical model predicted water flux using the membrane transport parameter without experimental data. But compared to mathematical model, machine learning model provided better prediction accuracy for the water flux and operating pressure, showing the high potential of the machine learning application. Although machine learning provided very good accuracy, I think it has also limitation, because we need good data for high accurate model development. Okay, thank you for the listening.
Thank you, Simi, and thanks for keeping the time. I think we have time for one or two questions, please. Any questions?
Thanks for the understanding, Morgan. Just wondering, you mentioned there's old models based on the lab scale reactors. What's the difference of the pilot and lab scale settings? I mean, what do you make to make a new one for pilots?
In case of the lab scale test, it just uses very small size of membrane. So if you use the small size of membrane, the concentration change in inlet and outlet is very small. So it is difficult to identify the change of the concentration. But if you use very large membrane area like the 7 square meter, or we use up to the 63 square meter membrane area, you can identify the very big difference between inlet and outlet. It is very useful to know that the concentration is changing in the real system, because F4 is normally used for the concentration of solution or dilution of solution. We can calculate using the batch scale, batch mode in the lab scale mode, but it is difficult to predict real performance. So it is better to conduct a pilot scale experiment to design the real system. And also, from the data using the lab scale test, it is difficult to get the design parameter. So it is better to have the pilot scale. Yeah. And also, from the mathematical modeling, it is actually it was very difficult to predict actual good accuracy. Actually, I like calculating, and also I expected very good accuracy from the mathematical model. For the mathematical model, we have to use the mass transfer coefficient. It should be obtained from the small scale lab scale test. But we try to get the best prediction result, but I hate to admit we could not get a very good accuracy from the mathematical model. Anyway, we will try to get the good result from the mathematical model, and maybe we can also find some insight why we cannot get the good accuracy from the mathematical model. Anyway, the machine learning showed a very good accuracy, and I think the combination between the mathematical and machine learning model can give more good insight for the practical use. Thank you.
Thank you. I'm afraid we don't have more time for questions, and that was a comprehensive answer. I will talk to you if you about questions I have later. But let's give a round of applause.